All right, this is the first video of a 3-video series, kind of about the derivative applications. This one is particularly about the chain rule, which is incredibly important as we move on and learn about how derivatives are useful outside of a math classroom. So now that we've kind of learned all of the derivative rules, there's just one more that we need, and it's called the chain rule. And we need this because so many real-world applications don't use friendly polynomials like x squared and sine of x, for example, or e to the power of x. They use more complicated things, and we need to be able to take a derivative of a composition function. And that's like f of g of x or something along those lines. Maybe even more complicated than that, where there's a few nested inside of each other. So something that's really useful is we often, when we refer to a derivative, we're taking the derivative of a function we call y. So the name of the function we call is y with respect to x. A lot of the times I will write d over dx of like x squared plus 3 because my function is y. And this is another way of writing dy dx. Well, it's really convenient to have dy dx because I'm taking the derivative of the function where my input variable is x. But what if we can't do that immediately? What if we don't have all of the pieces? It would be really, really convenient to have dy du and the derivative of some other function u with respect to x, because dy du times du dx, notice that this and this are the same, and when we multiply we can cancel things out like that, and so I get dy dx. So it's really valuable for us to have the derivative of the function y as we take the derivative of y with respect to some variable unknown u, and then we have u, which we know is the thing we're taking derivative of. We take du and take the derivative of that. And so if I multiply the derivative of y with respect to u and the derivative of that other function with respect to x, we get the function that I wanted to begin with, dy dx, which is really useful for us. And this may not make a ton of sense, so let me explain it in a slightly different way that hopefully will make a little bit more sense. So if I have a function like this, it may seem really easy just to take the derivative of, but notice that this is not as easy to do because I've got a function inside of another function. So I just wanted you to be aware that that is something that's happening here. So I'm looking for dy dx, but I can't take the derivative immediately. Now what I could do is I could expand this out into x squared plus 1 times x squared plus 1 times x squared plus 1, but that's a lot of work, and I don't want to have to do that every time. So here's the solution. The solution is that for this function, if I think about the inside as some u, and remember, we want to be able to do take the derivative of the function y with respect to u, and we also want to take the derivative of the function u with respect to x, so that when I multiply them together, I get dy dx. And that's our ultimate goal. So if I look at this, I think, oh, I've got this thing inside, that's going to be my u. That there's something there. So then, if that's u, then my function y is really and my function is really u to the power of 3, because u is this stuff over here, or the stuff inside, u cubed. So I've just assigned it separately. But then we can take du dx. So here is u. If I take the derivative of u on both sides, so I'll do that in a different color, du dx, du over dx, of this stuff, I get 2x. And if I take the derivative of y with respect to u, dy du, I get 3u squared. And so how do I put this all together? Well, I know what u is. This was u, this y equals x squared plus 1. This was u. So dy du is really the same as, here I'll do it in red, 3 times u. What was u? U was x squared plus 1 squared. But that's not it. That's dy du. And remember, we have to multiply dy du by du dx in order to get dy dx. So I have dy du. This is dy du, the derivative of y with respect to u. And now I have to multiply it by du dx. I have to multiply it by this du dx. And that is 2x. And this is called the chain rule. Now this seemed really complicated, but it's really not as complicated, so let's break it down really quickly. All I did was take the derivative of the outside and multiply it by the derivative of the inside. So, but here's the logic behind it. The dy du, the u's are going to cancel out, and I'm going to get dy dx. But I need to multiply it by the derivative of the inside guy in order for that to happen. I'll go over several more examples. Just bear with me. We're going to do one more this longhand way, and then we're going to slow it down and kind of make it routine, and so it's a little bit more easier. So if I want to find dy dx of this function, again, it's really challenging because I have a function inside of a function. I've got my u right there. Oop, I should actually do this real quick. I've got my u inside. So my u is going to be 3x minus 2x squared. And that makes my y u to the power of 3. Okay, remember dy du times du dx, those x's cancel out, so I get dy dx, which is really what I'm after to begin with. So I need the derivative of y with respect to u, so 3u squared, but we know that u is going to be that 3x minus 2x squared. So 3, I'm going to do it in blue, 3x minus 2x squared, back, to the power of 2, times, so this was this, dy du, and now I have to multiply it by du dx. Now, I don't have du dx yet, but I can get it really easily by taking the derivative of this top thing. If I take the derivative of this, I get this, and so I'm going to do that in blue. It's 3 minus 4x. So times 3 minus 4x. And the nice thing to do would be to make it a little bit cleaner, but for now we're just getting the theory and the understanding. And so this is dy dx because I've multiplied dy du and dy dx. Hopefully this logic makes sense, and if it doesn't, watch it again. Try and understand what is dy, what is du, what is dx, what are all of these pieces. What is the u piece, and how did I take the derivative of that? What is the y piece, and how did I take the derivative of that with respect to a different variable other than x? All right, so we're going to kind of go into just some practice a little bit more. And I'm going to give you some practice. I'm going to show you a few examples that come from our class textbook. Before I even begin, I want to spend some time just recognizing that this is an easier problem than it looks like. I don't actually need the quotient rule because I can rewrite this as negative 7 times 2t minus 3 to the power of negative 2 using my negative exponent rules. But then here's why the chain rule needs to happen is because I can't just take the derivative of this. This stuff is going to be my u. So let's do it in a slightly different manner. If I think about this as my function now, I'm kind of ignoring what was before. But if I think about the second thing as my function, I'm going to take the derivative of the outside. The outside is stuff squared to the negative second power. So I'm going to do negative 7 times negative 2 times the stuff to the negative third power. I just took the derivative of the outside guy. But now I need to use the chain rule and multiply it by du. So if this is u, I need du dt in this case. So du dt is just 2, so I need to multiply it by the chain of the stuff inside. So multiply it by 2. So my answer is going to be like this, and if I simplify it, I know that -7, -2, and +2 is 28, positive 28, 2t minus 3 to the power of -3. And if I wanted to be really nice, I would rewrite it as a fraction again. 2t minus 3 to the power of 3. And so this is my dy dx, or dy dt, because our variable here is t. My function is y, my variable is t, dy dt. So, just a summary, I took the derivative of the outside, and then I had to multiply it by the derivative of the stuff that was inside. The derivative of 2t minus 3 is just 2. And then I cleaned it all up. A few more examples. This one actually does require the chain rule, but it's a little bit more complicated because it now uses the quotient rule, and it has fractional exponents. So let's just try and take it as cleanly as possible. X squared plus 4. I just want to change that into a fractional exponent. And if I'm going to use the quotient rule, I'm going to do low d high. Well, low d high is x squared plus 4 to the half. Low times low d high, the derivative of the top is 1, minus high d low. This is where the chain rule comes in. High, the derivative of the bottom. So it's 1/2 stuff to the -1/2. I did the derivative of the outside guy. I'm going to do the chain rule in red. Now the derivative of the inside, 2x. The derivative of the inside is 2x. There's the chain rule in action. And last but not least, all over the bottom squared. Low squared. X squared plus 4 to the 1/2 squared. Well, that makes this really convenient. When I clean stuff up, I'm just going to reorganize this so my work is not disorganized. Just cleaning it up. X squared plus 4 times 1 is just to the 1/2. Minus, I've got an x and a 2x and a 2, so this and this cancel out, the 2, and I'm left with x squared. X squared plus 4 to the -1/2, all over, well, using my exponent rules, power to a power can just multiply, so I'm just left with x squared plus 4, and that's all that I have on the denominator, to the power of 1, because 2 times a half is 1. And for now, I'm going to leave it like this. I'm sure that we could simplify it more, but for the quotient rule, that's all I want to do. Just notice this chain rule happened because I took the power. I thought of this du. I needed to multiply by du, the derivative of the outside times the inside. So the derivative of the inside. All right, and sometimes the chain rule is kind of pesky because you got to use it more than once. You may need to use the chain rule twice or 3 or 4 times, just depending on how complicated things are. So I think about, hey, I've got stuff squared. So I'm going to just use the power rule first, and then I have to multiply it by the derivative of the inside. So hopefully this makes sense. I'm going to do 2 stuff to the power of 1, so 3x minus 1 over x squared plus 3 times, the chain rule says I need to take the derivative of the inside stuff. This was to the power of 1. Times the derivative of the inside stuff, which here, I got to use the quotient rule. Low d high, 3x minus 1 low times the derivative of the top, the low, oh my goodness. Low d high times the derivative of the top minus high d low, 3x minus 1 d ho, 2x over ho ho, x squared plus 3 quantity squared. So this is this part right here. This is the chain rule. And we could totally clean this up and make this much cleaner to work with, but for now I'm going to leave it right here just because the chain rule is complicated enough. I don't want to go too far with the algebra. This chain rule also works with trigonometry, and this is quite a simple one. But if I take the derivative of a sine function, let's say derivative of sine is cosine, so dy dx is gonna be cosine of the stuff times the chain rule is times the derivative of the inside, so times 2. So this becomes 2 cosine of 2x. Pretty straightforward. Once you understand what's the inside and what's the outside, I think the hardest part is understanding what's the inside, what's the outside. So cosine squared of x. Now this doesn't look like a composition function, but I would need to rewrite it to show you that, hey, this actually is a composition function because cosine squared x is really cosine x times cosine x. And so I could rewrite it as this, in which case, if I wanted to do dy dx, I'd need to take the derivative of the outside, 2 cosine x times the derivative of the inside, which is the derivative of cosine is negative sine of x. So I need to take the chain of the inside being this stuff in here. And for niceness purposes, let's clean it up to be, negative 2 cosine x times sine x. So someone doesn't get confused that this is still a multiplication problem. There's no addition or subtraction in here. So if we need to use the chain rule more than once, we run into that sometimes. So just again, I'm going to do it with the sine function because I think this will clean it up and it'll show you how it will need to be used more than once. So we'll clean it up. So I've got an outside function, which is stuff to the power of 3. And then I have a function inside of this sine function, which is this 4x stuff. So I will show you really quickly that I'll show it and try and do it in different colors each time. So I've got my dy dx. I'm going to take the derivative of my outside function, which is 3 times the sine of 4x squared. So I've taken the derivative of the outside guy. But now I need to multiply it by the derivative of sine of 4x. Okay, I've done it all in one step, but that's easier said than done. I just showed you what I'm about to do. I haven't actually done it yet. So I'm going to just copy everything down so far. So dy dx, I meant to do that in a different color. To do that in black, so dy dx, this is all the same. 3 sine of 4x squared times, now I'm going to do the derivative here. The derivative of sine of 4x is cosine of 4x times the derivative of the inside of 4x. Which we know to be 4. It's going to be 4. But we had to do that extra step, which may not seem super duper intuitive. So 3 sine of 4x, all of that squared, times cosine of 4x, and then the derivative of 4x is just 4. And if we wanted to clean it up, we would say 4 times 3 is 12. 12 sine squared of 4x times cosine of 4x. And it seems really messy, but notice that we had to do the chain rule twice. When we took the derivative of this, we needed to use the chain rule to do the derivative of this, and the derivative of this ended up being 4. So I hope that makes sense that this stuff, or I'll even mark it out, that this stuff is the first chain rule, and then the chain rule again happened here. So all of this is associated with the chain rule. And finally, we can do the derivative of exponents, but we also need the chain rule. I'm going to quickly state the derivative rule for exponential functions because we don't always see them. Some variable to the power of x is going to be the natural log of that value times the original function that we started with. So if I'm going to take the derivative of this function, so dy dx, if I'm using the chain rule, I know that I have to use the chain rule because my inside guy is this power of 7x. So my derivative is going to be the natural log of the base, which is the truth, which is what it normally is, natural log of the base, times the base, the regular what it normally is. But when I use the chain rule, I have to take the derivative of the inside, d over dx, the derivative of 7x, which we know to just be 7. So we've got 7 natural times the natural log of 2 times 2 to the 7x power. And this is the derivative of the original function. That chain rule is so critical because we forgot to take the derivative of the inside. It's 7 times bigger when the reality of the derivative is that it's 7 times bigger. And exponential functions come in many forms. Here we've got the derivative twice, so d over dx. And just remember that the derivative of a regular exponential function with a base e is e to the x. So if I take the derivative of the whole thing, I have to remember this is my inside stuff, this 4x squared. So my derivative is what it normally would be if I took the derivative of it, x squared, times the derivative of the stuff inside. Well, here I've got the chain rule again. So I have to use, if I do e to the power of 4x squared, this is the same as before. This was the chain rule the first time. The derivative of 4x squared is 2 times 4x squared. And then when we clean it up, it'll be done. So that's 8x squared e to the 4x squared. And there's lots of little numbers all over, but that's dy dx. The chain rule is for all functions, and whenever a function lives inside of one another, we call those composition functions. And sometimes composition functions are more complicated than others. The chain rule is so incredibly useful, and it will lead to a lot of other very, very, very powerful mathematics that we can do with calculus that help us relate this outside of a math classroom. So I hope this video was helpful. I know that it's complicated at first, but the more you practice the chain rule, the easier it becomes. So please take some time there's hundreds of examples online. Take some time to find those and practice with them. You'll really be glad you did.